Shear force and bending moment diagrams are powerful graphical methods that every mechanical and civil engineer should know how to use to analyze a beam under loading. In this video, I'll explain exactly how to master these diagrams, and we will see how they can be used to understand how a beam is loaded. I want to start by explaining what shear forces and bending moments actually are. When a beam is loaded, internal forces develop within it to maintain equilibrium. These internal forces have two components. We have shear forces, oriented in the vertical direction, and we also have normal forces, which are oriented along the axis of the beam. If the beam is sagging, the top of the beam will get shorter, and so the normal forces in the top of the beam will be compressive. The bottom of the beam will get longer, and so the normal forces in the bottom of the beam will be tensile. Each of the tensile normal forces has a corresponding compressive force, which is equal in magnitude but opposite in direction. As such, these forces don't produce a net normal force, but they do produce a moment. This means we can conveniently represent the internal forces acting on the beam cross-section using just two resultants. One, shear force, which is a resultant of the vertical internal forces, and one bending moment, which is a resultant of the normal internal forces. This is a very common way of representing the internal forces within a beam. Drawing the shear force and bending moment diagrams is just figuring out what these internal forces are at each location along the beam. These resultant shear forces and bending moments will depend on the loads acting on the beam and the way in which the beam is supported. Beams can be loaded in a number of ways, the most common being concentrated forces, distributed forces, and concentrated moments. Beams can also be supported in a number of different ways. They can have pin supports, roller supports, or be fully fixed, which each restrain the beam in different ways. Pin supports prevent vertical and horizontal displacements, but allow rotation. Roller supports prevent vertical displacements, but allow horizontal displacement and rotation. Fixed supports prevent all displacements and rotation. If a certain degree of freedom is restrained at a support, we will have a corresponding reaction force or reaction moment at that location. For example, rotations are permitted for a pin support, so there is no reaction moment, but displacements in the vertical and